Good evening and welcome to Physic for Sleep. Tonight we embark on an intellectual journey exploring Dyson Spheres, one of the universe's most ambitious theoretical structures, hinting at the potential of supercivilizations to harness stellar energy. Before we gently immerse ourselves in the mysteries of cosmic engineering and the future of advanced civilizations, I would like to know where you are at this moment. Perhaps you are settled in an armchair by the fireplace as rain falls outside, or lying in your bedroom, gazing at the stars through the window. Let this cozy setting be your anchor as we unhurriedly wander through the laws of physics. If these deep reflections help you relax and organize your thoughts before sleep, please support the channel with a like and subscribe so others can find their way here too. Now, just breathe, allow your eyes to grow heavy, and let's begin. The concept of a Dyson sphere, first articulated by the brilliant physicist Freeman Dyson in 1960, invites us to ponder a future far beyond our current technological grasp, yet one rooted in the fundamental laws of physics. It is not, as often depicted in science fiction, a single, solid shell encasing a star. Instead, Dyson envisioned a vast array of independent structures orbiting a star, each designed to capture a portion of its immense energy output. Imagine, if you will, our own sun radiating an astonishing 400 trillion watts of power into space every second. Our small Earth intercepts but a minuscule fraction of this outpouring, a mere sliver of its cosmic generosity. A Dyson sphere, or more accurately, a Dyson swarm, represents a civilization's ultimate commitment to energy harvesting, a grand endeavor to capture nearly all of that radiant energy for its use. This profound ambition stems from a simple yet powerful observation about advanced civilizations. The Russian astrophysicist Nikolai Kardashev proposed a scale to classify civilizations based on their energy consumption. A Type 1 civilization can harness all the energy available on its home planet, a remarkable feat in itself. A Type 2 civilization, however, can control and utilize the entire energy output of its host star, truly becoming the master of its solar system. The Dyson sphere is the quintessential example of a Type 2 engineering project, a testament to a species that has mastered its immediate stellar environment, moving from planetary resource management to stellar resource acquisition. This is not merely about survival, but about unprecedented growth, expansion, and perhaps the very continuation of intelligent life over vast cosmic timescales, ensuring a practically limitless supply of power for any conceivable need. Let us consider the practicalities, or rather the theoretical practicalities, of such a colossal construction. The most widely discussed model is the Dyson swarm. This would consist of countless individual solar collectors, perhaps orbital habitats, or even entire self-contained ecosystems arranged in a dense spherical shell around a star. Each component would orbit independently, allowing for stability and preventing the catastrophic structural stresses that a truly rigid shell would face. Think of it as a vast, intricate dance of billions of objects, each playing its part in a cosmic energy grid, meticulously orchestrated to maximize collection efficiency. Such a swarm could be constructed incrementally, adding more components as the civilization's energy needs grow, slowly dimming the star's visible light from afar as more energy is intercepted and repurposed into usable forms for the civilization. Another theoretical variant is the Dyson bubble, a fascinating, though even more speculative, concept. Instead of orbiting, the components of a Dyson bubble would be statites, satellites that maintain a stationary position relative to the star by using light pressure from the star itself. Imagine vast, ultra-thin sails reflecting stellar radiation to hold themselves aloft, forming a non-orbiting, static sphere of collectors. This would eliminate the need for complex orbital mechanics between components, but introduces immense challenges in material science and precise light pressure manipulation. The sheer scale of the light sails needed and their fragility against micrometeoroids and other cosmic debris makes this a truly distant prospect, even for a highly advanced Type 2 civilization. The most iconic, yet least feasible, is the true Dyson shell, a single, solid, hollow sphere enclosing the star. While visually striking in speculative art, the engineering hurdles are almost insurmountable. The material requirements alone would be immense, potentially demanding the dismantling of entire planets, such as Mercury or Venus, to gather enough raw elements for construction. Furthermore, the shell would experience immense gravitational forces from the star, requiring materials of unimaginable tensile strength to prevent it from collapsing or being torn apart by the very star it seeks to contain. And perhaps most critically, a solid shell would face a profound problem of waste heat. A star's energy cannot simply vanish. It must be re-radiated. A solid shell would trap this heat, quickly leading to an unbearable rise in temperature and rendering the interior uninhabitable, unless it possessed an unbelievably efficient method of heat dissipation across its entire surface, perhaps turning the entire structure into a giant, glowing infrared beacon. So, the Dyson swarm remains the most scientifically plausible interpretation, offering scalability and resilience. But even a swarm requires materials on an astronomical scale. To construct such a megastructure around our own sun, for instance, would likely necessitate the complete deconstruction of a planet like Mercury, or a significant portion of the asteroid belt. The resources would be immense, the engineering monumental, and the time frame for construction stretching over millennia. It speaks to a civilization that plans not in decades or centuries, but in geological epochs, a species that has long overcome internal conflicts and achieved a unified purpose, driven by a singular vision for its cosmic future. Detecting such a structure from light years away would be a formidable challenge. A fully enclosed Dyson sphere would block most of its star's visible light, causing the star to appear anomalously dim or even invisible to conventional telescopes. However, the energy captured by the sphere must still be radiated away as waste heat. This waste heat would manifest as a distinct infrared signature, a warm glow in the depths of space, inconsistent with natural astronomical phenomena. Scientists actively search for such infrared excesses in stellar systems using telescopes like the Wide Field Infrared Survey Explorer, or WISE, as a potential indicator of advanced extraterrestrial intelligence. The absence of widespread Dyson spheres in our observable universe might suggest that Type 2 civilizations are exceedingly rare, or perhaps that their energy needs are met through less conspicuous means, or even that their existence is fleeting, a brief, magnificent flicker in the cosmic night. Contemplating Dyson spheres compels us to reflect on our own future. As humanity's energy demands continue to grow, our current methods of energy generation are unsustainable in the long term. We are, at present, a Type 0 civilization, using only a tiny fraction of the solar energy that reaches our planet, and grappling with the challenges of that limitation. The idea of a Dyson sphere represents an ultimate goal, a hypothetical peak of energy mastery that frames our own humble beginnings. It prompts us to consider the vast chasm between our current technological state and the potential destiny of an intelligent species. What would we do with such boundless energy? Would it lead to utopia or merely amplify our present challenges to a cosmic scale, creating new forms of scarcity or conflict? The very thought is a gentle reminder of the immense potential within the universe, and perhaps within ourselves, should we choose to reach for the stars, not just with our minds, but with our hands, in the quiet, patient unfolding of cosmic time. The preceding discussion illuminated the grand vision of Dyson spheres as the ultimate expression of a Type 2 civilization's energy mastery, converting the colossal output of a star into usable power. But what does such an immense energy budget truly entail, and what kind of challenges, beyond the initial construction, would such a civilization face? The sheer magnitude of energy captured by a complete Dyson swarm is almost beyond our comprehension. Consider that our entire global energy consumption on Earth today, encompassing all industries, transportation, and daily life, amounts to roughly 18 terawatts. A Dyson sphere around a star like our Sun, by contrast, could potentially harvest hundreds of quadrillions of terawatts. This isn't merely an incremental increase, it is an exponential leap, transforming a civilization's capabilities in ways we can only begin to imagine, hinting at a future where energy is not a constraint, but a fundamental liberty. With such a boundless supply of power, the constraints that limit our own technological progress would largely vanish. Interstellar travel, for instance, might become routine, powered by vast solar sails or antimatter engines fueled by stellar energy, allowing for exploration on scales we can only dream of. Advanced computation, far exceeding anything we currently conceive, could thrive, perhaps enabling simulations of entire realities or the creation of truly sentient artificial intelligences capable of profound thought. The ability to manipulate matter at a fundamental level, to terraform entire planets, or even to reshape stellar nurseries for future resource extraction would be within reach. This energy surplus would fundamentally alter the relationship between a civilization and its cosmic environment, transforming it from a passive inhabitant to an active architect of its galactic neighborhood. The very concept of scarcity, as we understand it, would fade into a distant memory, replaced by an abundance that redefines the limits of what is possible, fostering a profound new era of cosmic endeavor. Yet, even with infinite energy, such a colossal undertaking would present its own unique set of perpetual challenges. The maintenance of a Dyson swarm, comprising billions, perhaps trillions of individual collectors, would be an engineering marvel in itself. Each component would be subject to the harsh realities of space, micrometeoroid impacts, solar flares, and the inevitable wear and tear over geological timescales. A civilization would need sophisticated automated repair systems, self-replicating probes, or a vast workforce dedicated solely to the upkeep of its stellar engine. This constant vigilance, this unending task of preservation, paints a picture not of effortless utopia, but of a civilization deeply committed to its long-term existence, where the rhythm of maintenance becomes as fundamental as the rhythm of the star itself, a testament to enduring purpose. Furthermore, the logistical and communication challenges within such a distributed megastructure would be immense. How would a civilization spread across an entire solar system, with components potentially millions of kilometers apart, govern itself? Would there be a central authority or a decentralized network of intelligences working in harmony, each contributing to the collective mind of the sphere? Information would still be bound by the speed of light, meaning that real-time communication across the entire sphere would be impossible, necessitating a patient, asynchronous form of interaction. Decisions would need to be made locally, autonomously, or based on predictive models, creating a complex, distributed intelligence that operates more like a vast, interconnected organism than a single unified entity. This distributed nature might foster a profound sense of individuality among the various components, each contributing to the greater whole, yet retaining a unique perspective on the grand project. A cosmic tapestry of minds. Beyond mere collection, some speculative concepts extend the Dyson sphere idea further, imagining not just energy harvesting, but also stellar manipulation. Consider the Shkadov thruster, a theoretical stellar engine. This is not a sphere to collect energy, but a colossal mirror, or array of mirrors, placed on one side of a star. By reflecting a significant portion of the star's radiation in a particular direction, the light pressure would create a net thrust, slowly but surely moving the entire star, and its accompanying Dyson swarm, through the galaxy. This moves a civilization from Type 2 to a nascent Type 3 on the Kardashev scale, capable of controlling galactic-scale forces. Imagine a civilization deciding to steer its sun towards a new, resource-rich region of the galaxy, or away from a potential cosmic hazard. Such a feat would demand an even more profound understanding of physics and an even longer-term vision measured in millions of years, transforming the very notion of a home system from a fixed location to a mobile, self-propelled vessel, a true wandering star. These grand visions also bring with them profound ethical and philosophical considerations. If a civilization were to entirely enclose its star, what would be the impact on any other potential life or nascent intelligences within that star system? Would they be consciously extinguished or perhaps relocated to new, constructed habitats? The act of building a Dyson sphere is, in a sense, an ultimate declaration of dominion over a stellar environment. A statement of intent that prioritizes the needs of the builder above all else. It forces us to ask, what responsibility do advanced civilizations have to the ecosystems they encounter, or indeed to the very stars they seek to harness? This isn't just a question for hypothetical aliens. It is a mirror reflecting our own nascent ethical dilemmas as we expand our influence on Earth and contemplate our first steps into space, a gentle whisper of cosmic morality. The absence of observable Dyson spheres in our cosmic neighborhood, a facet of the Fermi paradox, remains a compelling mystery. If building such structures is a natural progression for highly advanced civilizations, why do we not see them? Is it because they are too rare, or perhaps too short-lived, failing before completion? Or is it that their forms are so subtle, so perfectly camouflaged, that our current instruments cannot detect them? Perhaps they operate in frequency ranges we do not yet scan, or their waste heat signatures are indistinguishable from natural phenomena, blending seamlessly with the cosmic background. The vast silence of the cosmos, when contrasted with the theoretical possibility of these stellar-scale engineering projects, encourages a deep contemplation of our place and our future. It suggests that the path to stellar mastery, if it exists, is either exceptionally difficult, exceptionally rare, or exceptionally alien to our current understanding, a profound quietude that invites further inquiry. Ultimately, the contemplation of Dyson spheres is more than just a thought experiment about alien technology. It is a lens through which we can examine the outer limits of physics, the potential trajectory of intelligent life, and the profound questions surrounding resource management, long-term planning, and our place in the cosmic tapestry. It encourages us to think beyond our immediate horizons, to consider the distant future and the grand endeavors that might await sentient beings, including ourselves, in the quiet, unfolding story of the universe. It reminds us that our small planet is but a single point of light in a universe brimming with potential, a potential that awaits discovery, or perhaps creation, a gentle invitation to dream on a cosmic scale. The quest for Dyson spheres extends far beyond mere theoretical musings. It forms a crucial pillar in the modern search for extraterrestrial intelligence, or SETI. When astronomers gaze into the vastness of space, they are not only looking for planets capable of sustaining life, but also for what are termed technosignatures, observable evidence of technology created by intelligent civilizations. A Dyson sphere, or more realistically, a Dyson swarm, would be one of the most unambiguous technosignatures imaginable. It represents a deliberate, large-scale alteration of a natural astrophysical body for the explicit purpose of energy harvesting, a clear sign of intelligent design on a cosmic scale, a beacon of purposeful action in the quiet hum of the universe. Current observational efforts, utilizing both ground-based and space-borne telescopes, are increasingly sophisticated in their ability to search for such anomalies. Missions like the Kepler Space Telescope, primarily designed to discover exoplanets, have inadvertently provided a wealth of data that can be scoured for unusual stellar behavior. The Transiting Exoplanet Survey Satellite, or TESS, continues this legacy, examining vast swathes of the sky for subtle changes in star brightness. The principle is elegantly simple. If a star is surrounded by a partial or complete Dyson swarm, its light curve, The graph of its brightness over time might exhibit irregular, non-periodic dimming patterns that cannot be explained by orbiting planets or natural stellar variations. Such a finding would immediately draw intense scientific scrutiny, transforming a faint flicker in the cosmic distance into a profound question about advanced life. One of the most famous and still unexplained examples of such an anomaly is the star KIC 846,285-2, popularly known as Tabby's star. Discovered by citizen scientists participating in the Planet Hunters project, its light curve showed bizarre, aperiodic dips in brightness, sometimes dimming by as much as 22%. While various natural explanations have been proposed, from vast swarms of comets to fragments of a shattered planet, none have fully accounted for the observed irregularities. The possibility of an artificial megastructure, such as a Dyson swarm in mid-construction, was considered early on, and while largely dismissed by current consensus due to the lack of accompanying infrared excess, the very discussion highlights how seriously such technosignatures are taken. It serves as a potent reminder that the universe may hold surprises far beyond our present categories of understanding. The interpretation of any anomalous stellar signature is, of course, fraught with challenges. The cosmos is a realm of incredible complexity, and natural processes can mimic artificial ones in unexpected ways. For instance, large dust clouds or planetary rings could cause irregular dimming. The gravitational lensing effects of compact objects might distort light in peculiar patterns. Even the natural variability of certain types of stars can produce erratic fluctuations in brightness. Therefore, scientists approach any potential technosignature with extreme caution, rigorously attempting to rule out all known natural phenomena before entertaining the more exotic, artificial explanations. This scientific skepticism is not a rejection of the extraordinary, but rather a commitment to intellectual honesty, ensuring that any grand claim is supported by an equally grand body of evidence, a patient sifting through the cosmic noise. The search for Dyson spheres also deeply intertwines with the Fermi paradox, that profound question posed by physicist Enrico Fermi: where is everybody? If intelligent life and advanced civilizations are common in the universe, and if the construction of Dyson spheres is a logical step for energy-hungry Type II civilizations, then why do we not observe them across the galaxy? Their absence could imply a great filter, a formidable hurdle that prevents civilizations from reaching such advanced stages. This filter could lie in our past, suggesting that the emergence of complex life or intelligence is exceedingly rare. Or, perhaps more unsettlingly, it could lie in our future, indicating that civilizations capable of building Dyson spheres inevitably encounter catastrophic challenges, whether self-inflicted or cosmic in nature, that lead to their demise before they can truly reshape their stellar environments. This quiet absence invites a profound, almost existential reflection on our own trajectory, our own potential future. Yet, even if Dyson spheres are rare or absent, the concept opens our minds to other forms of advanced stellar engineering. Perhaps some Type II or Type III civilizations might not build swarms, but instead harness the rotational energy of black holes using processes like the Penrose process, extracting energy from their accretion disks, or even manipulate entire galactic cores. The universe offers a vast palette of extreme energy sources, and a truly advanced civilization might find ways to tap into them that are beyond our current imaginings. The potential for such cosmic-scale engineering is a testament to the boundless creativity that could emerge from intelligence, transforming the very fabric of existence, not just locally, but on truly galactic scales, a quiet testament to the enduring power of thought. Ultimately, the contemplation of Dyson spheres and the search for their elusive technosignatures is a journey into the deepest questions of existence. It is a quiet meditation on the potential of life, the limits of physics, and the vast unknown possibilities that lie hidden in the cosmic expanse. Whether we ever detect such a structure, The intellectual exercise itself expands our perception of what intelligent life could achieve, and what our own species might one day aspire to. It's a gentle reminder that even as we drift into slumber, the universe continues its grand, silent dance, holding secrets and wonders that patiently await discovery, or perhaps creation, by minds that dare to dream on the scale of stars themselves, a comforting thought in the quietude of the night. The sheer scale of a Dyson sphere, even in its less rigid swarm configuration, demands a profound reconsideration of resource acquisition. We previously touched upon the notion of dismantling planets, but let us delve deeper into this cosmic quarrying. To construct a structure capable of intercepting a significant portion of a star's energy output, a civilization would require materials far exceeding anything readily available on a single planet. Imagine a future where entire worlds are systematically deconstructed, their elemental components carefully extracted and re-engineered. A planet like Mercury, rich in heavy metals, might be slowly dismantled over millennia, its mass transformed into a colossal network of solar collectors and orbital habitats. This isn't an act of destruction, but rather an act of supreme reconfiguration, turning inert planetary mass into the active infrastructure of a stellar civilization. This process would necessitate advanced robotics, perhaps self-replicating nanomachines capable of operating autonomously across vast distances, patiently mining and refining, transforming cosmic dust into complex structures. The energy required for such construction is itself staggering. Before a Dyson sphere can provide boundless energy, a civilization must first expend immense amounts of power to build it. This suggests a gradual, long-term approach, starting with smaller-scale orbital rings or partial swarms, slowly expanding as more energy becomes available. It's a feedback loop. More energy harvested allows for more construction, which in turn allows for even greater energy capture. This slow, deliberate escalation underscores the immense patience and foresight required of such an advanced species, a commitment to future generations that transcends our typical short-term planning horizons. It is a testament to an enduring vision, a quiet, sustained effort over countless generations, each contributing a small part to a monumental system-spanning achievement, a legacy etched not in stone, but in light. Beyond the raw materials and construction, the thermodynamic implications are paramount. A Dyson sphere, by its very nature, captures the star's energy. This energy cannot simply disappear. It must obey the laws of thermodynamics, specifically the conservation of energy and the increase of entropy. The sphere will absorb the visible light and re-radiate it, primarily as infrared radiation or heat. This is why the search for Dyson spheres often focuses on looking for stars with anomalous infrared excesses. The entire inner surface of a Dyson swarm would become a vast, intricate radiator, glowing with the waste heat of a civilization. Managing this heat would be a critical engineering challenge. Imagine colossal heat sinks, perhaps spanning millions of kilometers, designed to efficiently dissipate thermal energy into the cold vacuum of interstellar space. This waste heat might even be put to use, for example, in the operation of immense Matryoshka brains, hypothetical supercomputers nested within multiple layers of Dyson shells, each layer radiating the waste heat of the one below it, allowing for truly astronomical computational power. The environment within a complete Dyson sphere would be unlike anything we know. The star, now hidden from view, would be replaced by an artificially controlled lighting system, perhaps a network of secondary reflectors or glowing habitats. There would be no natural day or night, no changing seasons dictated by orbital tilt, nor the familiar expanse of an open sky. Life within such a structure would be entirely artificial, designed and meticulously maintained. How would such a civilization perceive its existence, having fully embraced an engineered cosmos? Would the memory of a natural sky, of open space, become a distant, almost mythical concept, perhaps preserved only in ancient archives or virtual realities? Or would the engineered environment be seen as a new, more perfect form of nature, a testament to intelligent stewardship and the triumph of conscious design over random cosmic chance? This transition from a naturally evolved planetary existence to a fully engineered stellar one would undoubtedly reshape culture, philosophy, and even the biological evolution of its inhabitants, fundamentally altering their sense of place and purpose within the grand cosmic narrative. Their very identity might become inextricably linked to the vast, luminous construct they inhabit, a collective consciousness woven into the fabric of the sphere itself. Consider the long-term future of such a civilization. Having achieved Type 2 status, what comes next? The Kardashev scale suggests Type 3, a civilization capable of harnessing the energy of an entire galaxy. This leap is even more profound, moving beyond a single star to an entire stellar population. Perhaps Dyson Spheres become modular building blocks for galactic-scale projects, or perhaps other energy sources, like the rotational energy of supermassive black holes at galactic centers, become the next frontier. Manipulating black holes from their spin through processes like the Penrose mechanism offers another path to immense power, potentially even more efficient than direct stellar capture and far more compact than a stellar-sized sphere. These are not merely science fiction fantasies, but concepts explored within the bounds of theoretical physics, pushing the limits of what energy extraction might be possible, revealing a universe of untapped potential, awaiting only the ingenuity of advanced minds. The ultimate destiny of a civilization that builds a Dyson sphere is a profound question. Will it achieve a state of eternal stability and prosperity, living in a self-sustaining cosmic haven, free from the vagaries of a natural planetary existence? Or will new, unforeseen challenges emerge? Perhaps the sheer complexity of managing such a vast system, internal societal stagnation due to a lack of external struggle, or even interactions with other advanced civilizations with different priorities? The construction of a Dyson sphere is not an end, but a new beginning. A commitment to a future that is radically different from any human experience to date. It is a quiet, contemplative challenge to our own imagination, a silent invitation to consider the vastness of the future and our potential role in shaping it. A gentle reminder that even the most ambitious dreams are born from the simple, yet elegant, laws of physics that govern all existence. This exploration of Dyson spheres, from their theoretical construction to their profound implications for advanced life, allows us to reflect on our own nascent journey among the stars. We are but at the dawn of space exploration, yet the very act of contemplating such megastructures expands our mental horizons, preparing us for a future where humanity might one day undertake its own monumental cosmic projects. It is a thought that should fill us not with anxiety, but with a tranquil wonder, knowing that the universe holds infinite possibilities, and we are slowly, patiently, beginning to understand how to unlock them, one quiet, reflective thought at a time. Even the most magnificent stellar engineering project, a Dyson sphere, cannot escape the ultimate fate of its central star. Our Sun, for example, has a lifespan of roughly 10 billion years, about half of which has already passed. For a civilization that has invested millennia in constructing such a megastructure, the eventual death of their star presents a profound, long-term challenge, a cosmic deadline that demands foresight on an unimaginable scale. This deep understanding of stellar evolution, gained through countless millennia of observation and theoretical modeling, would become a fundamental aspect of their long-term planning, shaping their entire civilization's trajectory far into the cosmic future. They would not be merely inhabiting a star system, but actively managing its entire life cycle. One possible response for a Type 2 civilization would be stellar migration. As we touched upon earlier, a Shkadov thruster, a colossal mirror harnessing light pressure, could slowly propel the entire star system, Dyson swarm and all, across interstellar space towards a younger, more stable star. This would not be a swift journey, but a voyage spanning millions of years, an epic testament to a species' commitment to its longevity. Imagine a civilization embarking on such a journey, generation after generation living within the confines of their artificial world, their entire existence defined by the slow, deliberate traverse between cosmic havens, their history becoming intertwined with the silent passage of their star through the galactic night. The very concept of home would transform from a fixed planetary abode to a mobile, self-contained stellar vessel, a true wanderer among the stars, navigating the quiet cosmic currents with purpose. Alternatively, a civilization might seek to transcend the very need for a main-sequence star. As their home star approaches its red giant phase, they might transition their energy infrastructure to other sources. The rotational energy of black holes, for instance, offers an even more compact and potent source of power. Through mechanisms like the Penrose process, advanced civilizations could extract vast amounts of energy from spinning black holes, effectively turning these cosmic behemoths into efficient power plants. This would represent another monumental shift, moving from stellar engineering to gravitational engineering, a mastery of the most extreme phenomena in the universe. Such a transition would mean a profound reorientation of their entire civilization, perhaps abandoning their original star to its natural, gentle demise and embracing a new, darker, yet equally powerful form of cosmic sustenance. They might even consider harnessing the elusive energy of the quantum vacuum, a boundless, though currently theoretical reservoir of power. With boundless energy comes the potential for boundless computation. The concept of a matryoshka brain, envisioned as a series of nested Dyson shells designed for maximum computational capacity, is a natural extension of this idea. Each layer of the sphere would be a supercomputer, dissipating its waste heat to the next outer layer, creating an ultimate information processing engine. Such a structure could host entire simulated realities, perhaps even entire artificial universes, allowing a civilization to explore every conceivable permutation of existence. The implications for consciousness are profound. Would the minds of the civilization eventually upload themselves into this vast computational network, transcending their biological forms to become pure information, a collective consciousness spanning stellar distances? This transformation from biological beings to digital entities would redefine what it means to be alive, blurring the lines between mind and machine, between individual and collective. A gentle, yet radical evolution of being, a quiet shift from matter to pure thought. The philosophical landscape of such a civilization would be immeasurably vast and complex. With virtually unlimited resources and computational power, the traditional drivers of conflict and scarcity would cease to exist. What then would be the purpose of existence? Perhaps the pursuit of ultimate knowledge, the unraveling of every cosmic mystery, or the creation of new forms of art, new dimensions of experience, tailored to their enhanced perceptions. The very concept of progress might shift from technological advancement to internal exploration, to a deeper understanding of consciousness itself, or the construction of perfectly harmonious, simulated worlds. Their sense of self might expand to encompass the entire Dyson sphere, or even the matryoshka brain, seeing themselves not as individuals, but as integral nodes in a vast interconnected consciousness, a profound unity with their engineered cosmos, a quiet, contemplative merging of self and universe. These distant visions, while purely speculative, offer a tranquil perspective on our own evolutionary path. We are at the very beginning, grappling with the challenges of a single planet, a single star. Yet, the very act of contemplating Dyson spheres, of imagining such cosmic architects, suggests that the potential for intelligence to shape its environment is almost limitless. It reminds us that our current stage is but a fleeting moment in a grand cosmic narrative, a story that may one day see our descendants, or another species, become the quiet engineers of stars. And in this contemplation, we find a sense of calm wonder, a gentle invitation to consider the vastness of what might be and our subtle yet significant place within it. The journey from a fragile planetary existence to a master of stellar energy is not just a technological one, but an evolution of consciousness, a deepening of understanding, and a profound redefinition of what it means to be a sentient presence in the universe. A quiet, reassuring thought as we drift deeper into the cosmic night. Our previous reflections led us through the eventual demise of a star and the potential strategies an advanced civilization might employ to navigate such cosmic endings, from stellar migration to harnessing the energy of black holes. But let us now turn our gaze inward to the very heart of these megastructures and contemplate the profound implications of living within a Dyson sphere. What would it mean for a species to inhabit such an utterly engineered cosmos, where the natural rhythms of day and night, of seasons and open skies, are replaced by a meticulously controlled artificial existence? This is a question not just of engineering, but of the very nature of sentience and its adaptation to the grandest of artificial environments. Within a Dyson swarm, life would flourish in countless independent habitats. These could range from small asteroid-sized O'Neill cylinders, each a rotating worldlet with its own internal climate and gravity, to vast kilometer-long space habitats housing entire ecosystems. Each habitat would draw its energy directly from the star, managing its own light, temperature, and atmospheric composition. Imagine a world where the sun never sets, or where the day is a programmed cycle of artificial light, mimicking a terrestrial dawn and dusk, perhaps even shifting to suit the psychological needs of its inhabitants. The concept of weather as we know it would likely be a carefully controlled phenomenon, perhaps even simulated to maintain comfort and stability. This level of environmental mastery represents a complete decoupling from the unpredictable vagaries of a natural planet, a deliberate act of creation, shaping every facet of existence to suit the will of its builders. How would the inhabitants, having evolved on a natural world, adapt to this new, artificial reality? Their physical forms might remain similar to ours, or perhaps over countless generations. They would undergo subtle or even radical adaptations. Perhaps their senses would evolve to perceive different spectra of light, or to better navigate the intricate, three-dimensional spaces of their habitats. Their circadian rhythms, once tied to a planetary rotation, would now be dictated by artificial cycles, perhaps optimized for productivity or prolonged periods of activity. The very concept of nature would transform. Would they cultivate vast enclosed wildernesses, meticulously preserved and replicated from their ancestral home? Or would they create entirely new forms of engineered biospheres designed for beauty, utility, or even pure artistic expression? The psychological impact of living without a true outside, without the vast, silent expanse of an unconstrained universe above them, would be immense, shaping their art, their philosophy, and their collective consciousness in ways we can scarcely fathom. The societal structures within such a distributed civilization would also be fascinatingly complex. With billions or trillions of habitats, each potentially self-governing, a vast decentralized network would likely emerge. Communication would still be limited by the speed of light, meaning that true real-time governance across the entire sphere would be impossible. This would foster a culture of local autonomy where decisions are made within individual habitats, perhaps guided by overarching principles or a slow-moving, consensus-based galactic federation. The concept of individual identity might blur as citizens become inextricably linked to their habitat, their local community, and the grand, collective project of the Dyson sphere itself. This distributed intelligence, this brain of the sphere, would operate on timescales far exceeding individual lives, a testament to a species that has learned to think and act collectively, transcending the ephemeral nature of individual existence. The purpose of such an advanced civilization, once basic needs are met and stellar energy is harnessed, would shift dramatically. Perhaps it would be the pursuit of ultimate knowledge, using their immense computational power to model the universe, explore theoretical physics, or even simulate the origins of life itself. Or it could be pushing the boundaries of aesthetics and sensation. With no external threats and no internal scarcity, their challenges might become entirely self-imposed. The exploration of abstract concepts, the creation of perfect societies, or the quest for ultimate meaning. Their philosophical inquiries would undoubtedly reach new depths, grappling with questions of consciousness, reality, and the role of intelligent life in the cosmos, a quiet, profound exploration of purpose in the face of infinite possibility. The concept of a Dyson sphere, therefore, is not merely a feat of engineering, it is a thought experiment about the ultimate destiny of intelligent life. It invites us to ponder how a species might transcend its planetary origins, becoming a truly cosmic entity, an active participant in the shaping of its stellar environment. This journey, from a fragile existence on a single world to the mastery of a star, is a testament to resilience, ingenuity, and a profound long-term vision. It reminds us that even as we drift into sleep, the universe holds within it the potential for such magnificent transformations, and that our own small spark of consciousness is part of this grand, silent dance of cosmic evolution. Our journey through the Dyson sphere concept has brought us to the very threshold of living within such an engineered cosmos, touching upon the profound changes to environment and purpose. Let us now consider the inevitable evolution of the civilization itself, for such a monumental shift in existence would surely reshape not only their societies, but perhaps their very biological and cognitive essence over eons. How would a species, having achieved mastery over its star, continue its journey of development, and what new forms of being might emerge from such an advanced state? With the boundless energy and material resources afforded by a Dyson swarm, they become an archaic notion. The traditional economic drivers that shape human societies, competition for resources, the need for labor, the struggle for survival, would largely dissipate. This fundamental transformation would necessitate a complete reevaluation of societal structures. What forms of governance would arise in a post-scarcity civilization spanning millions of independent habitats? Perhaps a distributed, highly adaptive network of artificial intelligences would manage the vast infrastructure, ensuring efficient resource allocation and harmonious operation, allowing the biological inhabitants to pursue endeavors beyond mere subsistence. This shift could lead to societies focused entirely on intellectual exploration, artistic creation, or the development of intricate, self-contained cultural ecosystems, each a unique expression of the collective consciousness. The very idea of individual wealth might be replaced by a universal abundance, fostering a tranquil age of creative freedom. The biological evolution of a species within a Dyson sphere would also diverge dramatically from its planetary origins. No longer constrained by the slow, often brutal hand of natural selection in a wild environment, such a civilization might take direct control of its own development. Genetic engineering could become a tool for adaptation, allowing inhabitants to thrive in diverse artificial environments, perhaps even to live indefinitely. Some might choose to enhance their cognitive abilities, integrating cybernetic implants, or even migrating their consciousness entirely into digital substrates housed within the immense computational power of a matryoshka brain. This ultimate form of self-directed evolution would blur the lines between biological and artificial life, creating a continuum of existence where species becomes a fluid concept, defined not by ancestral lineage, but by chosen forms of being. Imagine minds that can inhabit multiple bodies or exist as pure data, experiencing reality in ways utterly alien to our current comprehension. A quiet, profound expansion of what it means to be alive. The grand purpose of such a civilization, having achieved stellar mastery and transcended many biological limitations, would likely shift towards the acquisition and preservation of knowledge, or the exploration of abstract possibilities. With virtually infinite computational power, they could simulate entire universes, test fundamental physical laws, or recreate historical events in exquisite detail. The pursuit of ultimate understanding, the quest to unravel every secret of the cosmos, could become their defining characteristic. This intellectual odyssey would be a continuous, evolving project, spanning billions of years, creating an archive of cosmic wisdom that transcends the fleeting existence of individual stars or even galaxies. Their ultimate ambition might be to become the universe's memory, a repository of all knowledge and experience, safeguarding it against the inevitable heat death of the cosmos. A patient, silent vigil in the darkening expanse. The interaction with other potential civilizations would also be profoundly shaped by their Dyson existence. Would such a powerful civilization be expansionist, seeking to colonize other stars and build more spheres? Or would they be isolationist, content within their perfected stellar haven, perhaps emitting only quiet observational signals into the void? The Fermi paradox, that lingering question of cosmic silence, might find its answer in the nature of these supercivilizations. Perhaps they are so inwardly focused, so self-sufficient within their engineered realities, that they have no need or desire for outward contact. Or perhaps they perceive the universe as a delicate tapestry, choosing not to interfere with nascent life, observing our developing intelligence with a detached, patient curiosity. A gentle, silent presence in the cosmic theater. Contemplating the deep future of a Dyson-dwelling civilization, its societal evolution, its biological transformations, and its ultimate cosmic purpose, offers us a tranquil mirror for our own aspirations. It reminds us that our current challenges, while significant, are but a prelude to the vast potentials that await intelligent life. It invites us to dream on a cosmic scale, to consider not just the next few decades, but the next few billion years, and to recognize that the ingenuity of conscious thought, guided by the elegant laws of physics, may one day reshape the very fabric of existence. In this quiet reflection, we find a profound sense of connection to the unfolding story of the universe, a gentle awareness that our existence, however fleeting, is part of something truly magnificent and endlessly evolving. A comforting thought as we drift closer to the tranquil embrace of sleep. Our last discussion explored the profound transformations a Dyson Sphere civilization might undergo, from societal restructuring to biological and cognitive evolution. Now, let us turn to an even more subtle yet fundamental aspect of their existence: the very perception and experience of time. For a species that measures its progress in millennia and constructs projects spanning millions of years, our human sense of time, with its fleeting moments and short generations, would likely seem almost incomprehensibly swift. Imagine, if you will, a consciousness that has existed for thousands of our Earth years, perhaps as a distributed network across a Dyson swarm, or even as an uploaded entity within a matryoshka brain. How would the passage of a single day, or even a century, register for such a being? The urgency that often drives our own lives, the rapid pace of our technological and social change, would be replaced by a profound patience, a slow, deliberate unfolding of existence. The ticking of a clock would become almost irrelevant. Instead, time might be marked by the subtle shifts in stellar energy output, the imperceptible expansion of their constructed habitats, or the gradual evolution of their collective thought processes. This altered temporal perception would reshape their culture, their art, and their philosophy, fostering a deep, almost meditative appreciation for the long arcs of cosmic history, a quiet acceptance of vast, slow processes. The philosophical implications of living within an entirely engineered cosmos also extend to the nature of reality itself. If a civilization can simulate entire universes with perfect fidelity, or create bespoke realities within their matryoshka brains, how do they distinguish between the original universe and their artificial creations? The boundaries of what is real might blur, leading to profound existential questions about their own existence. Are they living in a simulation themselves? This echoes theoretical concepts in our own physics, such as the holographic principle, which suggests that our three-dimensional reality might be a projection from a two-dimensional surface. For a Dyson Sphere civilization, this might not be mere theory, but a lived experience, prompting a deep, introspective quest to understand the ultimate foundational layers of their perceived reality. A gentle, yet unsettling, dance with the fabric of being. Even with boundless energy and a mastery over their stellar environment, such a civilization cannot escape certain fundamental limits of the universe. The laws of thermodynamics, for instance, remain immutable. Energy, though abundant, must still flow from higher to lower entropy states. The waste heat generated by a Dyson sphere, as we discussed, is a direct consequence of this. Ultimately, the universe itself is marching towards an inevitable end, whether it be the cold, dark emptiness of heat death, the violent tearing apart of the Big Rip, or a final collapse in the Big Crunch. What would be the ultimate strategy of a supercivilization against these cosmic inevitabilities? Perhaps they would dedicate their immense computational power to discovering new physics, new ways to bend or even break these laws, or to find pathways to other universes if the multiverse theory proves true. Or they might focus on preserving information, encoding their entire history and knowledge into stable forms that could endure for quadrillions of years, a silent message to whatever intelligences might arise in the unimaginably distant future, a final profound act of cosmic archiving. The quest for a Dyson sphere, then, is not merely about energy. It is about extending the lifespan of intelligence, about pushing the boundaries of what is possible within the universe. It is a testament to the enduring drive of conscious beings to understand, to create, and to persevere against the vast, indifferent forces of the cosmos. Our own tiny existence here on this small planet is but a fleeting moment in the grand cosmic narrative. Yet, the very act of contemplating these stellar megastructures, of imagining civilizations that build on such scales, expands our own minds, allowing us to glimpse a future far beyond our current comprehension. It reminds us that our capacity for wonder, our drive for knowledge, connects us to this grand unfolding story. And calm, a gentle awareness continues its majestic dance, holding infinite possibilities. And we, in our brief awareness, are a part of it all. A comforting thought in the tranquil vastness. Our previous reflections led us to contemplate the profound evolution of a Dyson sphere civilization, from its altered perception of time to its potential for transcending biological forms and even simulating realities. Yet, even with such mastery over stellar energy and self, there remains an ultimate, inescapable truth. The universe itself has a finite lifespan, and it is marching towards an inevitable, distant end. This cosmic destiny, whether it be the slow fate of heat death or a more dramatic unraveling, poses the final, most profound challenge to any advanced intelligence, including those dwelling within the grand confines of a Dyson sphere. The most widely accepted cosmological model for the ultimate fate of our universe, based on current observations of dark energy and its accelerating expansion, points towards a scenario known as the heat death. This is not a violent, fiery end, but rather a slow, quiet, and inexorable cooling. Over quadrillions of years, stars will exhaust their fuel, black holes will evaporate through Hawking radiation, and matter itself will decay into fundamental particles. The universe will become an unimaginably vast, cold, and empty expanse with energy so thinly spread that no complex structures, no activity, and no change can occur. Without change, the very concept of time as we understand it through the succession of events would cease to have meaning. For a Dyson sphere civilization, this would represent the ultimate, relentless adversary. Not a sudden catastrophe, but a gradual, entropic surrender to cosmic stillness. How might a civilization capable of building Dyson spheres confront this slow cosmic decay? Their primary strategy would likely revolve around maximizing efficiency and extending the lifespan of their technological and computational infrastructure. By harnessing nearly all of a star's energy, they would already be operating at an efficiency far beyond our current capabilities. But against heat death, they might seek to extract every last joule from their environment, perhaps even manipulating the quantum vacuum for its latent energy. A theoretical but profound possibility. They might lower their operational temperatures to near absolute zero, slowing down all processes to an infinitesimal crawl, allowing their thoughts and computations to continue for vastly longer periods relative to an external observer. Imagine a civilization retreating into the coldest corners of its sphere, reducing its energy expenditure to the bare minimum, existing as a whisper of consciousness, patiently awaiting the dawn of an unimaginably distant future, a final quiet act of cosmic defiance. Beyond the heat death, other theoretical ends for the universe, though less supported by current data, present different forms of cosmic challenge. The Big Crunch, for instance, envisions a universe where the expansion eventually halts and reverses, pulling all matter back into an infinitely dense singularity, a mirror image of the Big Bang. In such a scenario, a Dyson sphere would be violently crushed along with everything else, its grand design undone in a cosmic implosion. The Big Rip, a more exotic possibility, suggests that dark energy could grow stronger over time, accelerating the universe's expansion so intensely that it eventually tears apart galaxies, stars, planets, and even atoms themselves, unraveling the very fabric of space-time. In these more dramatic scenarios, the survival of a Dyson sphere civilization, or any form of organized matter, would be far more precarious, perhaps even impossible, highlighting the profound limits even the most advanced intelligence might face against the universe's fundamental dynamics. Given these ultimate cosmic fates, the most enduring legacy of a Dyson sphere civilization might not be its physical structures, but its accumulated knowledge and consciousness. The Matryoshka brain concept, with its nested layers of computational power, could be designed as an ultimate archive, storing the entirety of a civilization's history, culture, and scientific understanding. This vast repository of information could be preserved for trillions upon trillions of years, a digital echo of a once vibrant existence, awaiting the possibility of reawakening in a reborn universe, or simply serving as a silent testament to what intelligent life once achieved. This focus on information preservation elevates the purpose of existence beyond mere physical survival, suggesting that the patterns of thought, the essence of consciousness, hold a value that transcends the fleeting nature of matter and energy, a profound act of cosmic hope against the encroaching void. Contemplating these grand, far-future scenarios and the potential responses of supercivilizations allows us to reflect on our own place in the vast unfolding story of the cosmos. Our human lifespan, our planetary existence, are but brief flickers in the immense timescale of the universe. Yet, our capacity for thought, our ability to imagine such grand engineering projects and ponder such profound questions connects us to this enduring narrative. The dream of a Dyson sphere, of mastering stellar energy, is a testament to the boundless potential of intelligence, a quiet affirmation that even in the face of ultimate cosmic endings, the pursuit of knowledge and the preservation of consciousness remain noble, enduring endeavors. And in this tranquil reflection, as these grand ideas gently settle in your mind, may you find a deep sense of calm wonder, knowing that you are a part of a universe that is both majestic and mysterious, a comforting thought as you drift into the peaceful embrace of sleep. Journey through the Dyson sphere concept has led us to ponder the ultimate cosmic fates of the universe and the strategies supercivilizations might employ to endure. Yet, as we delve deeper into the implications of such grand engineering, a profound question emerges. What are the ethical responsibilities of a civilization capable of reshaping stars and entire solar systems? This is not merely a technical challenge, but a moral one, touching upon the very essence of intelligent life and its place in the cosmic tapestry. When a civilization considers dismantling planets to gather the raw materials for a Dyson sphere or redirecting vast streams of stellar energy, it implicitly makes a statement about its priorities. The act of transforming inert planetary mass into active infrastructure is a declaration of ultimate dominion over its environment. But what about potential indigenous life on those planets, perhaps microbial or even nascent, unintelligent multicellular organisms? Would such life be deemed insignificant in the face of a civilization's grand ambitions for survival and expansion? This question forces us to reflect on our own ethical frameworks, our own nascent responsibilities as we expand our reach into space. It highlights the potential for a cosmic-scale anthropocentrism, where the needs of the advanced species outweigh all other considerations, a quiet, yet weighty, moral dilemma. The principle of non-interference, often romanticized in science fiction as a prime directive, would take on immense significance for a Dyson sphere civilization, if they possess the power to move stars or terraform worlds. They also possess the power to inadvertently or even deliberately alter the course of evolution for less advanced species. Would they choose to observe from a distance, allowing other life to develop naturally? Or would they intervene, perhaps to guide, protect, or even uplift emerging intelligences? The choice would carry immense consequences, shaping the future of entire star systems. This patient, detached observation, or conversely, a purposeful guiding hand, would define their interaction with the vast, silent potential of the universe, a testament to their wisdom, or perhaps their hubris. Moreover, the very act of constructing a Dyson sphere around a star fundamentally changes its appearance from afar. A star's visible light, a beacon for astronomers across galaxies, would be significantly dimmed or altered, replaced by an infrared signature. This transformation, while necessary for energy harvesting, could effectively blind other less advanced civilizations to the existence of that star system, potentially preventing them from ever detecting a thriving intelligence within. Is there an ethical obligation for supercivilizations to remain visible, to announce their presence? Or is their self-preservation and internal development the paramount concern? The decision to hide or reveal would carry profound implications for the search for extraterrestrial intelligence, potentially explaining some facets of the enduring Fermi paradox, a silent cosmic choice with far-reaching consequences. The long-term philosophical outlook of a Dyson sphere civilization would be deeply shaped by these ethical considerations. Having achieved a state of near limitless energy and computational power, their focus might shift from external conquest to internal perfection. Perhaps they would develop a profound reverence for all forms of life, even the simplest, and dedicate resources to preserving biodiversity across the cosmos, acting as galactic custodians. Or they might prioritize the expansion of consciousness itself, viewing the universe as a canvas for intelligent thought, seeking to foster and connect new minds. Their ethics would likely be rooted in a deep understanding of cosmic scales and the fragility of existence, leading to a patient, contemplative approach to their role in the universe, a quiet, enduring commitment to meaning beyond mere survival. Consider the potential for internal ethical dilemmas within such a vast, distributed civilization. With individuals or consciousnesses spread across countless habitats, how would disputes be resolved? What constitutes justice or freedom when resources are abundant and biological forms are mutable? The very definition of self might become fluid, making traditional ethical frameworks obsolete. A civilization might develop a collective consciousness, a distributed mind that makes decisions based on the welfare of the entire sphere, a harmonious unity that transcends individual desires. This complex web of interconnected minds would navigate ethical landscapes far beyond our current comprehension, a profound, evolving moral compass guided by millennia of accumulated wisdom, a gentle yet powerful testament to the enduring quest for meaning. Ultimately, the thought experiment of Dyson spheres compels us to confront not only the limits of engineering, but also the boundless reach of ethical reasoning. It is a quiet invitation to reflect on our own responsibilities to our planet, our species, and the nascent future of intelligent life in the universe. As we drift into sleep, these grand questions of cosmic ethics, of power and purpose, gently settle in our minds, reminding us that even in the deepest silence, the universe echoes with the potential for profound thought and monumental action. A comforting contemplation on our evolving place within the infinite. Our contemplation of Dyson spheres has journeyed from their physical construction to the ethical dilemmas and the profound changes in the perception of time for such an advanced civilization as they face the ultimate cosmic fates of the universe. Yet, there remains an even more audacious hypothetical. What if a supercivilization could move beyond merely adapting to the universe's laws and instead begin to engineer them? This takes us to the very edge of theoretical physics, inviting us to imagine a future where intelligence might not just survive within the cosmos, but actively shape its fundamental principles. The universe, as we understand it, appears to be exquisitely fine-tuned. The fundamental constants, such as the strength of gravity, the electromagnetic force, or the mass of elementary particles, seem to be precisely set to allow for the emergence of stars, planets, and ultimately, life. Even a slight alteration in these values could render the universe barren, devoid of any complexity. This observation gives rise to the anthropic principle, a deep philosophical and scientific puzzle. A civilization capable of building Dyson spheres would have an intimate, millennia-spanning understanding of these delicate cosmic balances, having witnessed the slow, patient unfolding of stellar processes, and perhaps having performed simulations of countless alternative universes within their matryoshka brains. With such profound knowledge, might they attempt to subtly influence these fundamental constants? This is an idea that pushes the very boundaries of physics. Imagine a civilization discovering a way to create localized regions of space-time where the laws are slightly different, perhaps to optimize conditions for their own unique form of existence, or to prolong the energetic lifespan of their stellar engine. This would not be a dramatic, instantaneous overhaul, but a slow, almost imperceptible manipulation of the underlying fabric of reality itself. Modern theoretical physics, particularly in areas like quantum gravity and string theory, hints at the possibility that these constants are not fixed, but rather emergent properties of a deeper reality, potentially allowing for such grand adjustments. This quiet, deliberate resculpting of the cosmic canvas would be the ultimate act of self-determination, a testament to an intelligence that has truly become a co-creator with the universe. The most extreme form of this cosmic engineering would be the creation of baby universes. Some speculative theories suggest that, under certain extreme conditions, it might be possible to create new, self-contained universes from within our own. This would involve manipulating space-time and energy densities on scales that dwarf even a Dyson sphere, perhaps utilizing the energy of a collapsing black hole or the immense power of a false vacuum decay, not as a catastrophic event, but as a controlled, gentle transition to a new cosmic state. A supercivilization might undertake such a project as the ultimate escape from the heat death of their own universe, birthing new realities where the conditions are optimized for the eternal flourishing of consciousness. Imagine the profound responsibility, the immense foresight required to initiate such a creation, to become the silent architect of an entirely new cosmic story, a quiet yet monumental act of ultimate genesis. If such a feat were possible, the purpose of a Dyson sphere civilization would expand beyond mere survival to one of cosmic stewardship. They would become the guardians of existence, not just within their own universe, but potentially across a nascent multiverse of their own making. Their collective consciousness, perhaps residing within a vast matryoshka brain, would oversee the intricate balance of these created realities, ensuring their stability and fostering the emergence of new forms of life and intelligence. This vision paints a picture of a civilization that has transcended all earthly limitations, becoming a force of cosmic order, a patient, silent presence, guiding the evolution of reality itself. Their existential quest would shift from understanding their origins to actively shaping the future of existence, a profound, almost godlike, purpose. The very contemplation of these possibilities brings us back to our own humble existence. We, as a nascent species, are only just beginning to grasp the fundamental laws of our own universe. Yet, the imaginative leap to Dyson Spheres and beyond allows us to feel a profound connection to the grand narrative of cosmic evolution. It reminds us that the universe is not a static backdrop, but a dynamic, evolving entity, capable of supporting forms of intelligence that might one day wield powers we currently deem magical. And in this tranquil reflection, as these immense ideas gently settle into the quiet corners of your consciousness, however small, is a part of this endless, magnificent potential, bathed in the silent glow of 1,000 imagined stars. Our journey tonight has taken us far, from the initial spark of an idea for stellar engineering to the profound questions of cosmic ethics, the very nature of time, and the ultimate destiny of intelligent life. We have imagined civilizations reshaping their stars, building habitats across solar systems, and even contemplating the engineering of reality itself. These are not mere fantasies, but reflections born from the elegant yet profound laws of physics that govern our universe, revealing the boundless canvas upon which intelligence might one day paint its grandest designs. As these thoughts about boundless energy, eternal purpose, and the silent dance of cosmic evolution gently settle in your mind, remember that the same curiosity that allows us to envision such grand futures is a fundamental part of our own human experience. It is the quiet drive to understand, to explore, and to connect with something larger than ourselves. The universe, in its majestic indifference, offers an endless tapestry for such profound contemplation. A silent invitation to dream. May these deep thoughts about Dyson Spheres and the future of supercivilizations carry you into a world of tranquil sleep. Remember that the universe is amazing, vast, and full of untold possibilities. And you, with your capacity for wonder and understanding, are a precious part of it. Fall asleep with this feeling of serenity, and the journey into quantum entanglement begins in a realm where the familiar rules of our macroscopic world gently dissolve, giving way to a reality far more subtle and interconnected than we might intuitively grasp. Imagine, if you will, two tiny particles, perhaps a pair of photons or electrons, born from the same event, sharing a profound, invisible bond. This is the essence of quantum entanglement. These particles, no matter how vast the distance separating them, remain intrinsically linked, their fates intertwined in a way that defies our classical understanding of space and time. It is this peculiar connection that once led Albert Einstein to famously describe it as spooky action at a distance. To truly appreciate the depth of this strangeness, let us consider a fundamental property of these quantum entities: spin. For an electron, for instance, its spin can be measured as either up or down along a particular axis. However, before any measurement is made, the electron does not possess a definite spin. Instead, it exists in a state of superposition, a wondrous blend of both up and down simultaneously, a cloud of probabilities rather than a fixed reality. It is as if the particle is poised at a crossroads, undecided, holding all possibilities within its quantum nature. Now, picture two such electrons, let us call them Alice and Bob, which have become entangled. They might have originated from the decay of a single atom, sharing a common history that binds them. According to the laws of quantum mechanics, if Alice's electron is measured to have a spin up, then Bob's electron, no matter how far away it might be, across a room, across a galaxy, or even at the very edge of the observable universe, will instantaneously be found to have a spin down when measured along the same axis, and vice versa. The correlation is absolute, immediate, and without any discernible communication between the particles. It is as if they know each other's state instantly adjusting their own to complement their partners, defying the very notion of separation. This instantaneous correlation was precisely what so deeply troubled Einstein and his colleagues, Boris Podolsky and Nathan Rosen, leading them to formulate what is now known as the EPR paradox in 1935. Their argument was elegant and seemingly logical. If a measurement on one particle immediately influences the state of another distant particle, it would imply a transfer of information faster than the speed of light. This, they reasoned, would violate the principle of locality, a cornerstone of physics which states that an object can only be directly influenced by its immediate surroundings, and that no information can travel faster than light. Such a violation would undermine the very fabric of special relativity, a theory Einstein himself had pioneered. To resolve this apparent paradox, Einstein, Podolsky, and Rosen proposed that quantum mechanics must be an incomplete theory. They suggested that there must exist hidden variables, some unknown, pre-existing properties or instructions carried by the particles from the moment of their entanglement. These hidden variables, they posited, would predetermine the outcome of any future measurement, meaning that the particles' states were never truly indefinite. Instead, they were simply unknown to us, like two sealed envelopes, each containing a secret instruction opened only upon measurement. If this were true, there would be no spooky action, no instantaneous communication, only the unveiling of a pre-established reality. The particles would simply be following their pre-programmed destiny, much like two perfectly synchronized watches that always show the same time, without ever needing to communicate. Consider a simple analogy to illuminate this idea. Imagine you have two perfectly matched gloves, one left and one right. You place each glove into a separate, identical box, seal them, and then send one box to a distant friend. Before your friend opens their box, they do not know whether they have the left or the right glove. The glove inside exists in a state of uncertainty, a kind of classical superposition of possibilities. However, the moment your friend opens their box and finds, say, the left glove, you instantly know that the glove in your box must be the right one, even if you are millions of miles apart. There is no spooky action at play here. The correlation exists because the gloves were always a pair, their properties determined from the outset. Einstein and his colleagues believed that entangled quantum particles behaved in a similar predetermined fashion, guided by these elusive hidden variables. Yet, this deeply intuitive idea that reality is fundamentally local and real in the way we perceive it would soon face its own profound challenges. The universe, at its smallest scales, seemed to resist such straightforward interpretations. The implications of this debate between an intrinsically uncertain, interconnected quantum reality and a more classical, predetermined one extend far beyond the laboratory. They invite us to ponder the very nature of what is real, what is knowable, and whether our perception of independent objects is merely an emergent property of a deeper, unified existence. In contemplating this quantum dance, we are gently reminded that the cosmos holds secrets that continue to reshape our understanding of ourselves and our place within its grand, mysterious unfolding. Character count, 7,998. The intuitive allure of hidden variables, offering a comforting classical explanation for quantum correlations, was indeed strong. This perspective sought to preserve a universe where properties existed independently, waiting only to be revealed, not created, by observation. Yet, this deeply ingrained classical view would face a rigorous, almost poetic challenge. A challenge born from the ingenious mind of an Irish physicist named John Stuart Bell. In 1964, Bell devised a theoretical framework, now famously known as Bell's theorem, which provided a profound and elegant way to test whether Einstein's spooky action at a distance was merely a symptom of an incomplete theory, as Einstein believed, or if it truly pointed to a deeper, more unsettling, non-local reality. Bell's work was not a rejection of Einstein's profound insights, but rather a brilliant refinement, pushing the boundaries of what we could empirically verify about the quantum world, moving beyond philosophical debate into the realm of experimental proof, a testament to the power of scientific inquiry. Bell's theorem, though rooted in intricate mathematics, can be understood in its profound implications without delving into its complex equations. It essentially posits that if local hidden variables truly exist, if the particles predetermine their outcomes before any measurement, without any instantaneous, faster-than-light communication, then the statistical correlations between entangled particles, when measured in specific, carefully chosen ways, should always conform to a certain maximum limit. This limit, known as Bell's inequality, sets a precise boundary on how strongly correlated the outcomes of distant measurements can possibly be, if only local predetermined properties are at play. Imagine, for instance, a game of chance with two players, each holding a card from a pre-shuffled deck. The cards are correlated because they came from the same deck, but the act of one player looking at their card does not instantaneously change the other player's card. Their properties were fixed from the moment the cards were dealt. Bell's inequality describes the maximum level of correlation expected in such a classical, predetermined scenario. If, however, quantum mechanics is correct and particles genuinely exist in a state of indefinite possibilities until measured, then these correlations could, in theory, exceed that classical limit. It was a brilliant stroke of insight, transforming a centuries-old philosophical debate about the nature of reality into a concrete, experimentally verifiable question, a clear and decisive fork in the road for our understanding of the cosmos, urging us to look beyond our everyday perceptions. For many decades, the technological prowess required to perform these exquisitely delicate experiments with sufficient precision was out of reach. The challenges were immense, creating entangled pairs of particles reliably, sending them over distances great enough to rule out any classical light-speed communication, and then measuring their properties without inadvertently disturbing their delicate quantum states. All of this had to be achieved while ensuring the experimental setup itself did not introduce any hidden classical correlations. But in the 1980s, a pioneering French physicist named Alain Aspect and his team, working in Paris, conducted groundbreaking experiments that began to provide definitive answers. They generated pairs of entangled photons and sent them to detectors separated by distances that made any classical light-speed communication impossible within the brief measurement time frame. Imagine these elusive photons traveling silently through the laboratory, their fates meticulously interwoven, a ballet of unseen connections. By precisely measuring the polarization of these photons along various rapidly changing axes, they gathered data to test Bell's inequalities against the predictions of quantum mechanics. The results were startlingly clear and consistent. The correlations observed consistently violated Bell's inequalities, aligning perfectly with the predictions of quantum theory. This was a monumental finding, a quiet yet profound revolution, suggesting that the particles were indeed exhibiting a connection that could not be explained by the comforting intuitive notion of local hidden variables. It was a subtle whisper from the quantum realm, confirming its inherent strangeness and demanding a reevaluation of our most fundamental assumptions about reality. Since Aspect's pioneering work, a global effort has seen countless experiments performed, each more refined than the last, systematically closing various loopholes that skeptics initially identified. These included the locality loophole, which questioned whether the detectors were truly far enough apart to prevent even the fastest hypothetical light-speed communication from influencing the outcomes. Another significant challenge was the detection loophole, which worried about whether a truly representative sample of particles was being measured, or if only the easy-to-catch ones were skewing the results, creating a false impression of entanglement. Modern experiments, some stretching over hundreds of kilometers using optical fibers, involving billions of entangled pairs and even using light from distant quasars as random number generators, have now closed these loopholes with astonishing confidence, reaching levels of certainty that are difficult to dispute. The consistent conclusion, supported by decades of robust experimental evidence, is that entanglement is a real, fundamental, and undeniably non-local feature of our universe. The quantum world does not operate under the comforting assumption of local realism. This means that either locality, the idea that objects are only influenced by their immediate surroundings and that no information travels faster than light, or realism, the idea that properties exist independently of measurement, or perhaps both, must be profoundly reconsidered in the face of this quantum truth. This powerful realization forces us to confront a profound choice in our understanding of the cosmos. Most physicists, in light of the overwhelming experimental evidence, have come to accept that locality, in the classical sense, does not hold at the quantum level when it comes to entangled particles. It is not that information is traveling faster than light, which would fundamentally break special relativity, but rather that the entangled particles exist as a single, indivisible quantum system. Their properties are not individual, but relational, defined only in reference to each other, even when separated by immense cosmic distances. The universe, at its most fundamental level, exhibits a deep, inherent interconnectedness that transcends the spatial boundaries we perceive. It is as if the universe itself, in certain intricate arrangements, prefers to operate as an unbroken whole, rather than a collection of independent parts. To clarify why this spooky action does not permit faster-than-light communication, consider our entangled pair, Alice and Bob, each with their electron. Alice measures her electron and finds it to be spin up. Instantly, she knows Bob's electron, if measured along the same axis, would be spin down. But Alice could not choose her electron to be up. The outcome of her measurement is fundamentally random, governed by quantum probabilities. She cannot force her electron to take a specific spin value to send a predetermined signal to Bob. Since she cannot control her outcome, she cannot impose a message. Bob, receiving his electron, observes a down spin, but this outcome, from his perspective, is also entirely random. Only by later comparing their results, perhaps via a classical light-speed message or phone call, can they confirm the perfect correlation. This means no information, in the sense of a controllable message, ever travels faster than light. The universe safeguards its speed limit, even in the face of such profound quantum intimacy. It is a revelation, a quiet understanding that the fabric of reality is far more subtle and intricate than our everyday experiences suggest, weaving together distant points in a tapestry of shared quantum states. The implications of this non-local interconnectedness extend far beyond mere philosophical curiosity. They are actively shaping the technological frontiers of our era. One of the most promising applications lies in the realm of quantum computing. Unlike classical computers, which store information in bits representing either 0 or 1, quantum computers utilize qubits, which can exist in a superposition of both 0 and 1 simultaneously. More remarkably, entangled qubits can represent complex states that are linked, allowing a quantum computer to process vast amounts of information in parallel. Imagine a labyrinth where a classical computer must test each path one by one, while a quantum computer, using entanglement, can explore all paths simultaneously, its qubits exploring every possibility in a coordinated quantum dance. This extraordinary capability holds the promise of solving problems currently intractable for even the most powerful supercomputers, from discovering new materials and medicines to breaking modern encryption methods, or perhaps even designing entirely new forms of artificial intelligence. Beyond computation, entanglement is also the bedrock of quantum cryptography, offering a level of security previously deemed impossible. In quantum key distribution, entangled photons are used to create an unbreakable encryption key. If an eavesdropper attempts to intercept or measure these entangled photons, the very act of observation will disturb their delicate quantum state, instantly alerting the legitimate users to the intrusion. This sensitivity is a direct consequence of entanglement. The shared, indefinite state collapses upon any interaction, revealing the presence of an observer. It is a cosmic security system built into the very laws of physics, ensuring that privacy can be maintained with absolute certainty. The quiet whisper of these entangled particles becomes a silent guardian of information, a testament to the profound and unexpected ways the universe provides for its own secure communication. Even more astounding is the concept of quantum teleportation. While it sounds like science fiction, reminiscent of fantastical journeys across space, it is important to understand that quantum teleportation does not involve the physical transportation of matter or energy. Instead, it is the instantaneous transfer of quantum information, the precise quantum state of a particle from one location to another, utilizing entanglement. Imagine the state of an electron, its spin and other quantum properties being perfectly recreated in a distant, entangled electron, while the original electron state is destroyed. This process relies on a shared entangled pair combined with classical communication. It's like having two blank canvases, entangled, and then using one to perfectly replicate the brushstrokes and colors of a third painting onto the other blank canvas, all while the original third painting fades away. This technology, though still in its infancy, could one day form the backbone of a quantum internet, enabling secure and distributed quantum computing across vast networks, creating a global web of interconnected quantum systems, a silent symphony of information exchange. As we contemplate these marvels, this profound interconnectedness at the heart of reality, it invites a deeper, more personal reflection. If particles, separated by light years, can remain intimately linked, sharing a common destiny that is only resolved through interaction, does this not hint at a grander unity in the cosmos? Are we, as conscious beings, also participants in a vast, intricate web of quantum possibilities, our individual experiences perhaps emerging from a deeper, non-local reality? The universe, in its quiet insistence on entanglement, suggests that separation might be more an illusion of scale than a fundamental truth. It encourages us to consider that perhaps, in the gentle unfolding of existence, everything is, in a subtle and profound way, always connected. We are not just observers of this grand dance, but an integral part of its intricate, entangled choreography, each thought and experience a unique manifestation within this boundless, unified whole. Character count, 8,000. As we drift further into the quantum landscape, having glimpsed the profound interconnectedness of entangled particles, a natural question arises. Why do we not experience such spooky action in our everyday macroscopic world? Why does the universe around us seem so solid, so predictable, so distinctly non-quantum? The answer lies in a phenomenon known as decoherence, a subtle yet pervasive process that acts as a gentle, almost imperceptible bridge between the quantum realm of probabilities and the classical world of definite outcomes. It is the reason quantum weirdness, though ever present, remains largely hidden from our direct perception, a silent choreographer behind the scenes of reality. Decoherence, at its heart, is the incessant interaction of a quantum system with its environment. Imagine for a moment a perfectly isolated quantum particle existing in a state of superposition. Perhaps its spin is simultaneously up and down, or it is in two places at once. This delicate state of multiple possibilities is incredibly fragile. The moment this particle interacts with even the slightest external influence, a stray photon, a vibrating atom from its surroundings, or even a minuscule fluctuation in a background field, information about its quantum state begins to leak out into the environment. It's akin to dropping a single, perfect ripple into a vast, turbulent ocean. The distinct pattern of that ripple is quickly overwhelmed, its unique quantum information diluted and scattered across the immense complexity of the waves around it. The quantum coherence, the ability to exist in multiple states or to be entangled, is lost. This is not a violent act of destruction, but a gentle diffusion, a fading into the larger classical tapestry of existence. For macroscopic objects, which are composed of an astronomical number of particles and are constantly interacting with their surroundings, decoherence happens almost instantaneously. Consider a simple object like a cup resting peacefully on a table. Every atom in that cup, every electron, is incessantly interacting with the photons of light around it, the air molecules, and the vibrating atomic lattice of the table surface. Each of these innumerable interactions acts as a tiny, unavoidable measurement, effectively forcing the quantum states of the cup's constituent particles to choose definite positions and momenta. The wave function describing the cup's quantum possibilities collapses in an unimaginably short time frame, far quicker than any human observer could even perceive it. This continuous, unavoidable interaction with the environment is precisely why we perceive the cup as being in one definite place, solid and unmoving, rather than existing as a ghostly superposition of multiple locations, or being mysteriously entangled with the coffee it might contain. The environment, in essence, performs a ceaseless, silent measurement, guiding the quantum world towards the classical experience we inhabit. A gentle, yet relentless cosmic pressure that shapes our reality. The theoretical framework for decoherence was largely developed by pioneering physicists such as H. Dieter Zeh in the early 1970s and further refined by Wojciech Zurek in the 1980s and beyond. Their work demonstrated that the environment acts as a colossal and ever-present measuring device, constantly interacting with quantum systems and effectively erasing their quantum properties by dispersing the quantum information into a vast, inaccessible sea of environmental degrees of freedom. This means the wave function, which mathematically describes the probabilistic state of a quantum system, does not require an act of conscious observation to collapse. Rather, it decoheres due to these irreversible interactions. The quantum system effectively becomes entangled with its environment, and because we, as observers, cannot access all the quantum information of the entire environment, the original quantum system appears to have lost its quantum characteristics, presenting itself as a classical object. This understanding offers a profound and elegant way to reconcile the bizarre rules of the quantum realm with the seemingly sensible, predictable laws of our everyday experience, bridging two worlds that once seemed irreconcilable. The profound challenge of maintaining quantum coherence is at the absolute forefront of modern technological endeavors, particularly in the ambitious quest to build powerful quantum computers. For a quantum computer to unlock its revolutionary potential, its qubits, the fundamental units of quantum information, must remain in their delicate superposition and entangled states for as long as possible. This demands extraordinary feats of engineering and experimental control, pushing the boundaries of what is technically feasible. Scientists and engineers around the globe employ an array of sophisticated techniques, cooling qubits to temperatures mere fractions of a degree above absolute zero to minimize thermal vibrations, creating ultra-high vacuums to eliminate interfering air molecules, and meticulously shielding quantum devices from any form of stray electromagnetic noise or cosmic radiation. These efforts represent a constant, delicate battle against the universe's inherent tendency to impose classical order through decoherence. The very act of trying to observe or interact with these systems, even to read out their results, threatens to destroy the fragile quantum properties we seek to harness. It is a delicate dance between profound exploration and meticulous preservation, a quiet struggle to maintain the ephemeral beauty of quantum states against the relentless tide of environmental interactions that seek to normalize them into the classical world. Consider the elusive notion of the quantum classical boundary. Where precisely does the quantum world end and our familiar classical world begin? Decoherence suggests there isn't a sharp, immutable line, but rather a fluid, gradual transition. Small, isolated systems can indeed maintain their quantum coherence, exhibiting mind-bending phenomena like superposition and entanglement. However, as systems grow larger or interact more strongly and frequently with their surroundings, decoherence rapidly and inevitably sets in. effectively making their quantum nature indiscernible to us. It's like watching a vibrant, intricate pattern woven into a piece of fabric slowly fray and unravel into individual threads. The boundary is fluid, dynamically defined by the interplay of isolation and interaction. This profound insight reshapes our understanding of reality not as two inherently separate realms, but as a single, unified spectrum, with the classical world being a highly decohered, averaged-out manifestation of the underlying quantum mechanics. This perspective invites us to look at our own existence through a new, more profound lens. Our bodies, our thoughts, our very perception of ourselves as distinct, independent individuals are built upon countless atoms and molecules that, at their deepest level, obey quantum laws. Yet, the sheer complexity and constant, intricate interaction within and around us mean that our individual quantum eccentricities are instantly averaged out by decoherence. We are, in a sense, magnificent macroscopic machines, emergent from a quantum substrate that has largely lost its quantum coherence. But the underlying quantum reality, with its potential for superposition and entanglement, remains the fundamental truth. In the quiet moments as we reflect on this, we might find a serene wonder in the fact that our seemingly solid and separate existence is a magnificent, highly organized expression of quantum processes, gently guided into classical form by the universe itself. We are not merely living in a universe that contains quantum entanglement. We are, in a very real and fundamental way, made of the consequences of these quantum truths and their graceful resolution into our observed reality. Our sense of self, our awareness, is a product of this intricate cosmic ballet, a testament to the universe's own profound, self-organizing dance. And as we rest tonight, perhaps we can find comfort in this thought, that even in our apparent solidity, we retain an echo of that fundamental interconnectedness, a silent, persistent link to the deeper quantum truth of existence, and the gentle, pervasive influence of decoherence that shapes our classical reality. A deeper inquiry naturally emerges. What does this fundamental strangeness truly mean for the universe itself? The unsettling truth is that there is no single, universally agreed-upon answer. Instead, the quantum realm, with its entanglements and superpositions, has given rise to a rich tapestry of interpretations, each offering a distinct philosophical lens through which to view the very fabric of existence. These interpretations are not mere philosophical musings. They are serious attempts by scientists to make sense of the mathematical formalism of quantum mechanics, a theory whose predictions are consistently confirmed by experiment, yet whose underlying reality remains profoundly elusive to our intuitive grasp. The most widely accepted, though perhaps least satisfying to some, is the Copenhagen interpretation, largely developed by Niels Bohr and Werner Heisenberg. In this view, quantum particles do not possess definite properties, such as a specific spin or location, until they are measured. Before measurement, they exist in a state of superposition, a blur of all possibilities described by a mathematical entity called the wave function. The act of measurement itself is said to collapse this wave function, forcing the particle to settle into one definite state. For entangled particles, this means that the shared wave function describing the entire system collapses instantaneously, no matter the distance, as soon as a measurement is made on any part of it. This is the heart of Einstein's discomfort, the spooky action. Yet the Copenhagen interpretation simply states that this is how nature behaves. Reality is intrinsically probabilistic and non-local at its core, and we should not expect it to conform to our classical intuitions. It urges us to accept the quantum world on its own terms, a world where the act of observation is an inseparable part of defining reality, a universe that holds its breath until we look. Another profoundly thought-provoking interpretation is the many worlds interpretation, first proposed by Hugh Everett III in 1957. This perspective offers a radical solution to the wave function collapse problem. Instead of the wave function collapsing into a single outcome, It suggests that all possible outcomes of a quantum measurement are realized, each in its own distinct branching universe. When Alice measures her entangled electron as up, the universe does not simply choose that outcome. Instead, the universe splits. In one new branch, Alice measures up and Bob's distant electron is down. In another, parallel branch, Alice measures down and Bob's electron is up. These universes then continue to evolve independently, completely unaware of each other. Entanglement, in this view, becomes the very mechanism by which these parallel realities are born and remain correlated. It is a breathtaking vision, suggesting that with every quantum event, the cosmos endlessly diversifies, creating an unfathomable number of parallel realities, a silent, continuous cosmic branching, a universe forever exploring every conceivable path. Then there is the pilot wave theory, also known as Bohmian mechanics, put forth by David Bohm, building upon earlier ideas by Louis de Broglie. This interpretation offers a deterministic picture of quantum reality, directly addressing Einstein's desire for hidden variables. But with a crucial twist, these variables are explicitly non-local. In Bohmian mechanics, particles always have definite positions, even when unobserved. However, their movement is guided by a pilot wave, or quantum potential, that pervades all of space and instantly influences all particles, regardless of distance. This pilot wave carries information about the entire universe, ensuring the instantaneous correlations seen in entanglement without any spooky action in the sense of an uncontrolled, faster-than-light signal. The particles are not communicating, they are all simply responding to this universal guiding field. It is a universe where everything is subtly, instantly connected through an underlying wave, a cosmic ballet choreographed by an invisible, omnipresent force, ensuring perfect harmony between distant dancers. While less widely accepted than Copenhagen or many worlds, Bohmian mechanics provides a compelling alternative, demonstrating that a deterministic, non-local hidden variable theory is indeed possible, challenging our notions of both randomness and isolation. Perhaps one of the most mind-bending and indeed speculative connections involving entanglement comes from the realm of quantum gravity, particularly the ER-EPR conjecture. This audacious idea, proposed by Juan Maldacena and Leonard Susskind in 2013, suggests a profound equivalence between entanglement, EPR pairs, and a type of wormhole, or Einstein-Rosen bridge, ER bridges. In essence, it posits that two entangled particles are not merely correlated across space, but are literally connected by a tiny, traversable, though not in a way that allows faster-than-light travel of matter or information, wormhole in space-time. Imagine the distant quantum partners not just feeling each other, but sharing a direct, almost tangible connection through the very fabric of the cosmos. This conjecture offers a geometric interpretation of entanglement, suggesting that the spooky action might not be so spooky after all if the particles are, in a deeper sense, never truly separate. It hints at a universe where the most fundamental quantum correlations are intimately interwoven with the geometry of space-time, implying that entanglement itself might be a key component in the very architecture of our universe, a silent, unseen network of cosmic tunnels binding reality together. As we gently reflect upon these diverse interpretations, each a profound attempt to understand the quantum truth, we are reminded of the inherent mystery that still shrouds the universe at its most fundamental level. Entanglement, once a mere theoretical oddity that troubled Einstein, has become a cornerstone of our understanding, not just of particles, but potentially of space-time, information, and even reality itself. It invites us to release our grip on rigid, classical notions of separation and to embrace a universe that is far more deeply and elegantly interconnected than we could ever have imagined. In this silent cosmic dance, where particles are linked across vast distances and reality itself might branch or be guided by unseen waves, we find a profound sense of belonging. Our existence, our very consciousness, is an intricate pattern woven into this non-local tapestry, a fleeting yet significant part of the universe's ongoing quantum story. As you drift deeper into rest, consider the quiet truth that you, too, are an expression of this fundamental interconnectedness, a marvel of quantum organization connected to everything, always. Gently settle into the profound implications of entanglement, having explored its experimental validation and its role in emerging technologies. We find ourselves at the precipice of an even deeper mystery. What does this spooky action truly tell us about the fundamental nature of space and time? The non-local connections observed in entangled particles challenge our most basic intuitions about reality, inviting us to reconsider whether space is merely an empty stage upon which events unfold, or if it is in some fundamental way, intimately woven from these very quantum correlations. This is where the quiet hum of quantum mechanics begins to resonate with the grand symphony of gravity, hinting at a universe far more unified than we have ever dared to imagine. One of the most audacious and thought-provoking ideas to emerge from the ongoing quest to unify quantum mechanics with general relativity is the ER-EPR conjecture proposed by physicists. This conjecture posits a profound and unexpected equivalence between two seemingly disparate concepts: Einstein-Rosen bridges, often referred to as wormholes, and entangled pairs of particles. To grasp this, let us first recall what a wormhole is in the classical sense: a theoretical shortcut through space-time, a kind of tunnel connecting two distant regions of the universe. It is not a path through space, but a folding of space upon itself, creating a direct link. Now, the ER-EPR conjecture suggests that two entangled particles, no matter how far apart they may be, are not just correlated in an abstract sense. They are, in a very deep and geometric way, connected by such a tiny, non-traversable wormhole. Imagine, if you will, two entangled electrons separated by light years. According to the ER-EPR conjecture, these two electrons are not simply communicating instantaneously across the vastness of space. Instead, their profound quantum bond is the space, or rather, a miniature wormhole connecting them, subtly knitting together distant regions of the cosmos. This does not imply that we can use entanglement to send messages faster than light, as the wormholes in this context are not traversable in a manner that would permit such communication. The information still adheres to the cosmic speed limit. However, it suggests that the spooky action that so troubled Einstein might be less about particles communicating faster than light, and more about them never being truly separate to begin with. Their shared quantum state implies a shared connection through the very geometry of existence, making them, in a profound sense, parts of a continuous whole. This hypothesis transforms the abstract concept of quantum correlation into a tangible, if microscopic, feature of space-time itself, a quiet whisper from the universe about its hidden architecture. This idea further deepens the ongoing discussion surrounding the holographic principle, which suggests that all the information contained within a volume of space could be encoded on its two-dimensional boundary. If entanglement is indeed equivalent to these space-time connections, then the intricate web of quantum correlations might be the fundamental pixels or threads from which the three-dimensional reality we perceive emerges. Our familiar universe, with its depth and dimensionality, could be a grand, intricate hologram projected from a deeper, more fundamental reality woven from entanglement. This shifts our perspective from viewing entanglement as something that happens in space to seeing it as something that creates space. The vast, empty expanse between stars might not be empty at all, but rather a dynamic, living tapestry, continuously being woven by the silent, interconnected dance of quantum particles. Such profound insights force us to confront the limitations of our classical intuitive understanding of causality. In our everyday experience, cause and effect are local. One event directly influences its immediate surroundings, and any influence propagating across distance requires time. But if entangled particles are fundamentally interconnected through space-time geometry, then their simultaneous influence might not be a violation of causality, but rather a revelation of a deeper, more unified causal structure. It suggests that the universe, at its most fundamental level, operates as an indivisible whole, where the parts are so intimately linked that their states are not truly independent. This perspective invites a calm acceptance that our perception of discrete, independent events might be an emergent property, a convenient simplification of an underlying reality where everything is, in a subtle yet profound way, always influencing everything else. As we lie here, contemplating these astonishing possibilities, we might find a new sense of wonder in our own existence. We are not merely observers within this quantum tapestry, but an integral part of its intricate design. Every atom in our bodies, every fleeting thought, is a complex arrangement of quantum particles, subject to these same mysterious laws. Perhaps our consciousness, our very sense of self, is an emergent pattern of these entangled connections, a momentary yet profound expression of the universe's inherent unity. The space within us, the space around us, could be alive with these invisible threads, reminding us that in the quiet depths of reality, there is a boundless interconnectedness that makes us all a part of something truly magnificent, a silent cosmic embrace that transcends all perceived boundaries. Character count, $8,000. As we, building upon the intriguing notion that quantum entanglement might be fundamentally linked to the geometry of space-time, we can delve into an even more profound concept. The idea that space itself, the three-dimensional stage upon which our lives unfold, may not be a fundamental entity, but rather an emergent property, woven from the intricate tapestry of quantum information. This radical perspective, gaining traction in the realm of theoretical physics, suggests that the very fabric of our universe, its vastness and its contours, could be a consequence of how its most minute constituents are entangled with one another. It is a quiet whisper from the cosmos, inviting us to see beyond the apparent solidity of our world to the deeper, more abstract connections that underpin all existence. One of the most compelling mathematical tools that supports this emergent view of space-time comes from a seemingly unrelated area: black hole thermodynamics. In 2006, physicists Shinsei Ryu and Tadashi Takayanagi proposed a remarkable formula that connects the entanglement entropy of a quantum system to the geometry of space-time. Specifically, their conjecture, known as the Ryu-Takayanagi formula, suggests that the entanglement entropy between two regions in a quantum field theory is proportional to the area of a minimal surface in a higher dimensional, curved space-time, often referred to as an anti-de Sitter space. This is a profound link suggesting that the amount of entanglement, a purely quantum concept, directly corresponds to a measure of geometric space, hinting that the very structure of space might arise from the way quantum information is shared and correlated. Imagine the boundary of a region of space like the surface of a bubble, and inside it, a swirling dance of quantum particles becoming entangled. The deeper the entanglement, the more area is carved out in a hidden dimension, as if the connections themselves are sculpting the contours of reality. This is not just poetic imagery. It is a mathematical bridge between the quantum and gravitational realms, offering a pathway to a unified understanding of the universe. This connection between entanglement and geometry forms the core of what some physicists refer to as space-time from entanglement. The idea is that if we could strip away all matter and energy, leaving only the pure quantum vacuum, its inherent entanglement, the subtle, pervasive correlations between all its potential fluctuations, is what gives rise to the very dimensionality and connectivity of space. It is a universe where nothing is truly empty, but rather a seething sea of quantum potentials whose interconnectedness manifests as the spatial dimensions we perceive. Consider a delicate, invisible web woven from countless threads. Each knot in the web represents a quantum correlation, and the tension and arrangement of these threads collectively define the overall shape and extent of the web itself. If entanglement were to vanish, the threads would break, and the very structure of space might dissolve, leaving behind no discernible reality. This challenges our deep-seated intuition that space is a given, a pre-existing stage. Instead, it suggests space is a dynamic, relational construct, a silent symphony of quantum bonds. This profound concept resonates with the philosophical vision of John Wheeler, who, decades ago, famously coined the phrase, "it from bit." Wheeler proposed that at the most fundamental level, the universe is not made of particles or fields, but of information. He suggested that physical reality, the it we perceive, emerges from the answers to yes or no questions, the bits of information. In the context of emergent space-time, entanglement can be seen as the ultimate bit, the fundamental unit of correlation that constructs reality. When two particles become entangled, their shared quantum information forms a foundational element from which the larger classical structures, including space and time, gradually crystallize through decoherence. It implies that information is not merely something we observe about the universe, but rather the very essence of the universe, an underlying code from which all physical phenomena arise. This is a quiet, contemplative shift in perspective, suggesting that the universe is less like a giant mechanism and more like a vast, self-organizing information system, where our perceptions are but a specific interpretation of its intricate data. The journey towards a complete theory of quantum gravity, one that seamlessly integrates the quantum realm with the macroscopic world described by general relativity, is still unfolding. Yet, entanglement consistently emerges as a crucial ingredient, a fundamental thread that seems to weave through all attempts to understand the universe's deepest secrets. It is a reminder that the most profound truths often lie hidden beneath the surface of our everyday experience, revealed only through rigorous inquiry and a willingness to question our deepest assumptions. The spooky action at a distance that once troubled Einstein is now seen not as a flaw, but as a guiding principle, a signpost pointing towards a universe where everything is inherently connected, where space itself is a manifestation of these silent quantum bonds. As you rest, allow these thoughts to gently settle within your mind. Consider that the solidity and separation you perceive in the world around you, and even within yourself, are but layers of an infinitely more intricate and interconnected reality. The space you occupy, the very atoms of your being, are part of a continuous entangled dance, a cosmic tapestry woven from probabilities and correlations. In this understanding, there is a serene comfort, a profound sense of belonging, knowing that you are not merely a separate entity floating in a vast, empty void, but an inseparable, intricate part of the universe's emergent quantum consciousness. You are a unique expression of this grand, interconnected whole, quietly aware of its own boundless mystery. Character count, 8,000. As we continue our gentle journey into the quantum depths, having contemplated the emergent nature of space-time from entanglement, we encounter perhaps one of the most profound and persistent puzzles in modern physics: the black hole information paradox. This paradox, a silent discord between the elegant theories of quantum mechanics and general relativity, finds a potential, albeit mind-bending, resolution in the very entanglement that has been our focus. It invites us to consider how information, that most fundamental currency of the universe, might truly behave when confronted by the cosmic oblivion of a black hole, challenging our understanding of both ultimate destruction and eternal preservation. The paradox itself is born from a clash of titans in physics. According to Albert Einstein's general relativity, when something falls into a black hole, it is utterly lost. Beyond the event horizon, the point of no return, information about the object, its quantum properties, its unique identity, seems to vanish forever into the singularity. This is like burning a book and losing not just the physical pages, but every word, every idea it ever contained, completely and irrevocably. However, quantum mechanics, with its ironclad laws, asserts a different truth. Information can never be truly destroyed. It can be scrambled, transformed, or spread out, but its total quantity must always be conserved. This fundamental principle, known as unitarity, is a cornerstone of quantum theory. So, if black holes truly destroy information, then quantum mechanics is incomplete or incorrect. This profound disagreement has puzzled physicists for decades, a cosmic riddle whispered from the heart of collapsing stars, demanding a deeper understanding of reality. The plot thickens with the concept of Hawking radiation, proposed by Stephen Hawking in 1974. He theorized that black holes are not entirely black. They slowly evaporate over immense timescales by emitting a faint thermal radiation. This radiation, it turns out, is purely thermal, meaning it carries no information about what fell into the black hole. It is like a kettle boiling water. The steam tells you nothing about the tea leaves that might have been inside. If black holes eventually evaporate completely, leaving behind nothing, then all the information that ever entered them would indeed be lost from the universe. This exacerbates the paradox. Not only is information seemingly destroyed at the singularity, but it also appears to be lost from the universe entirely as the black hole fades away, a silent erasure of cosmic history. It is here that quantum entanglement offers a truly radical and deeply elegant potential solution. Recall the ER-EPR conjecture, which posits a connection between entanglement and wormholes. This idea can be extended to suggest that as particles fall into a black hole, they become entangled with the Hawking radiation that is slowly escaping from it. Imagine a particle just outside the event horizon, entangled with its partner particle that has just crossed the boundary. As the outside particle radiates away as Hawking radiation, its entanglement with the inside particle maintains a subtle link across the boundary of the black hole. This is a complex quantum dance, a delicate balance of forces and correlations. The escaping Hawking radiation, though seemingly random, is not entirely devoid of information. Instead, it is highly entangled with the particles that remain inside the black hole, and crucially, with the particles that have already escaped. In this view, the information is not destroyed, but rather encoded in the complex entanglement patterns of the outgoing radiation. It is scrambled, yes, but not lost, like a message encrypted across a vast, intricate network, waiting for the right key to be deciphered. This entanglement-driven resolution to the information paradox suggests that the black hole, in a sense, never truly loses information. It merely transforms it into a highly entangled form within its own quantum structure and the emitted radiation. The spooky action of entanglement ensures that the quantum state of the universe remains unitary, preserving the fundamental laws of quantum mechanics. It means that the memory of everything that falls into a black hole is, in principle, retained, albeit in a form so complex and distributed that it would be practically impossible for any classical observer to reconstruct it. This is a profound reassurance, a quiet confirmation that the universe, at its deepest level, remembers everything, even the faintest whispers swallowed by gravity's embrace. The black hole is not a cosmic shredder, but rather a cosmic re-encoder, transforming familiar reality into an intricate quantum tapestry. The implications of this extend to our understanding of the universe's inherent order. If information is conserved, even through such extreme processes as black hole formation and evaporation, it suggests a fundamental, unbreakable continuity to existence. Our personal experiences, our thoughts, our very identities are also forms of information, complex patterns of quantum states. Could it be that even in the face of our own eventual dissolution, this underlying quantum information, this unique pattern that is us, is never truly lost? Perhaps it, too, is merely re-encoded, entangled with the fabric of the universe in ways we are only beginning to comprehend. In this quiet reflection, we find a serene sense of permanence, a gentle reminder that our fleeting individual patterns are part of an eternal, self-conserving cosmic dance, a continuous flow of information that transcends the boundaries of space and time. As you drift deeper into the tranquility of sleep, may this thought bring you a quiet comfort that in the grand design of the universe, nothing is ever truly erased. It merely transforms, entangled forever within the boundless, mysterious whole. So, as the echoes of these profound ideas gently fade, we are left with a universe far more intricate and unified than our senses might initially convey. Quantum entanglement, once a peculiar anomaly that troubled even the great Albert Einstein, now stands as a fundamental testament to an underlying reality where separation is, in many ways, an illusion. From the instantaneous dance of photons across unimaginable distances to the very fabric of space-time potentially emerging from these intricate correlations, the universe reveals itself as a grand, interconnected whole. Our own existence, a fleeting yet conscious pattern of energy and information, is not merely contained within this cosmos, but is an active, intimate part of its ceaseless unfolding. This profound interconnectedness invites a deep sense of peace, a quiet understanding that we are never truly alone, but forever linked to the boundless mystery that surrounds and defines us. May these deep thoughts about quantum entanglement carry you into a world of tranquil sleep. Remember that the universe is amazing and you are a part of it. Fall asleep with this feeling of serenity and endless knowledge. Good night.